Hi guys, welcome to another session, another tutorial session in electric drives. We are continuing from where we left off the other time. There's been watch kindly go and watch the electric drives 1, electric drives 2. So this is our third session in the electric drives. Right. So there was an introduction in the previous videos, a quick recap. We saw the types of drives we have, classification of drives. We saw steady states. Yeah, so that was the last thing we did was the steady state criteria. The criteria for steady states. So we know that we said that TE is equal to DL plus J d omega dt. TE is our motor torque, low torque, and this is our moment of inertia J, and this is our acceleration. Okay. We know this equation. We wrote the other time that TE minus TL is equal to a J d omega dt. And we said when TE is bigger than TL, this side is positive, hence there is acceleration. When TE is lesser than TL, this difference gives us a negative value, hence there is deceleration. And when TE is equal to TL, this gives us 0. So there is no acceleration. And that means that the body is moving with a constant velocity or is at rest. And that is the steady state. So we established all these facts in the previous video, right? Now, say, for example, let's take, now, say we have a drive system, right? We have a drive system operating at some steady state speed, right? Now, when I subject the drive, when I subject the system to some form of disturbance, it will go through a transient stage and settle at a new speed within some time. I repeat, I'm saying that you have the drive operating at some steady state value, right? Now, when you subject the drive to some form of disturbance, it will go through some transient state, right? And settle at a new speed within some time. Within some time. Okay, so we can read from here. So it says that so these are the disturbance I'm talking about. Starting, braking, and speed control of drives result in mechanical transient, which can be obtained by integrating the equation of motion. Let's see something here. Now, from here, I can write that what TE minus TL is equal to J d omega dt. If I multiply this, I'll get what dt is equal to J over TE minus TL d omega. So if I want to find the time, I'll say what? I'll integrate both sides, right? So then I can say my t is equal to integral from some initial speed to some final speed. J is the constant, so I can bring J out here. 1 over TE minus TL d omega. So now, the time taken for the drive, right? The time taken for the drive to move from a particular speed and settle at a new speed, undergoing some transient stage, is given by this formula here. That T is equal to J integral from omega naught to omega I 1 over TE minus TL d omega. This is it here. Right. Now, if I mention that the drive is starting from standstill. Standstill means that the initial speed is 0. So I can write this equation as this J integral from 0, which is the standstill, to some speed. omega 1 over TE minus TL d omega. Let's pay attention here. Let's look here. Okay. Let's pay attention. Let's look here. Papa, let me check. Everybody right. Everything is okay. Sure. So now, so you can see that this is an integral. This is an integral here, right? Yes. So to compute this, to find the transient time, we have a number of ways we can compute this. So the first is using the numerical. No, I didn't spell it well. Sorry. The first is using the numerical or graphical method, right? The second is using the analytical method. And finally, linearization. Now let's pay attention. Let's see something here. Okay. All right. So this is what we have here. Okay. Now let me clean this part here. So we said that the transient time, right? The time to change from one position to another state, another position is given by this equation here. And to compute this equation, we can use either the numerical or graphical method, analytical method, or linearization. Okay. So now let's take the numerical or graphical method. Let's take the graphical method. The graphical method, yeah. Let's see. So I said that my t is equal to j integral omega naught to omega I 1 over dE minus TL d omega. Now what it means is that if I'm able to plot a graph, of this function here, 1 over TE minus TL against speed, right? And I find the area. So let me say the area under the curve here. This is the curve here. The area under this curve. And I multiply by this moment of inertia, I'll get a time. Does that make sense? Yes. Because we know that the area under a curve corresponds to the integral of the function. So the integral of this function is just the area under the 1 over t minus TL and omega curve. Right. So that's the first way, that's the first method we can use. But one thing you must know is that this TE and TL functions, they are nonlinear functions. They are nonlinear functions. Hence, they are complex and cumbersome, and it's difficult to integrate them. It's difficult to work with them. I get it. Yes. So it's difficult to use the graphical method, difficult to use the analytical method, which brings us to the linearization, which is the method that we'll be dealing with. So since they are nonlinear functions, what we do is that we will have to linearize them, right? You have to linearize the functions so that now they become like linear functions, and then you can work with them. Okay, so let's go to the slides and let's see. Everything I've said is just this. So it's just this. So you just have to read the side. We derive this function here. Once you can plot a graph of 1 over TE against TL, then you can have that. Let me see. Yeah. Oh, but I have the new slide. So you didn't show the new. This is the old slide. Okay. All right. So now you see that the analytical method, a solution of the equation is obtained by separating and integrating this. But this is rarely possible because there is either no analytical expression for TE and TL, or if there is such a formula, the integration cannot be performed. Exceptions is, so there are some exceptions, of course. One is the starting of DC motor with a constant flux, no load starting of an induction motor. These will be considered later. Right. So now, this is difficult to do. So the next thing we'll look at is linearization. Linearization. So let's take the linearization. Let's take the linearization. Okay. Now, with the linearization, a lot was done in the slides, right? But let me just break it down and just talk about the salient points. Yeah. Okay, now we said that what we can find the time, right? The time that it will take the drive to change position when there's a disturbance. Okay. So now, when there is a disturbance, we also know that what the drive will change speed. When there's a disturbance, the speed of the drive will change from some value and settle at another value. Let's pay attention here, right? So I can find an expression. For the speed. Let me say omega t, right? That describes the behavior of how the speed behaves. So I can have speed against time here. And if I know a function for how the speed behaves, right, then I can just find the corresponding time for any particular speed at all. Omega 1, any particular speed. So let's see. So the omega t, which is the speed function after a disturbance, is given by omega f plus omega I minus omega f e exponent minus t over tm. Let me call this my equation 1. Right. Now, this omega f is our final value, our final steady state value. Omega I is our initial steady state value. This t is a constant. This tm is the what? Is the mechanical time constant. Right. Now, what is this tm? Tm is given by j over k. Equation 2. We need just 3 equations from this. We know j to be moment of inertia, but what's k? K is given by dtl over the omega minus dte over the omega at omega is equal to the final steady state value. Equation 3. Know that it's always TL minus E, because in alphabet L is bigger than E. You can think of it that way, that L comes before L is bigger than E. There's always L before E comes. That's a very easy way to recall. Okay, so now the speed, this is the speed after disturbance. Speed after disturbance, when you go to the transient stage, this speed function describes how the speed behaves. Okay, so we are linearizing it. Now, this Tm, we said, is the mechanical time constant given by J over K. What is the K? You differentiate the TL function with respect to omega, differentiate TE function with respect to omega, subtract them, and wherever you see an omega in the function, put the final steady state value. And we know that what? At the final steady state value, what? TE is equal to TL. So that will help us find the steady state value. So a steady state, TE is equal to TL. Now, these 4 equations will help us deal with questions involving this linearization and mechanical transient thing. These 4 things will help us deal with that. So now let's see. So you see, everything here is just working at deriving everything I've written down. This is just the mathematics part of it. Yeah. We will not deal with that. We will not deal with that. Let's move on. Uh, what- So everything here is just working at deriving that functions, right? This is a function. This is the speed that I discovered. This is what we have. Now, all these cases can be converted into numerical examples. So I want to look at these cases here. We'll just take numerical examples straight for it. Okay. So all these are just to explain what happens. But once we have numerical examples, we can deal with it easily. So let's move on. All right. So let's take numerical examples. Let's move on. Okay. So let's see. We have this here. A DC shunt motor has a speed torque equation given by this. So we've been given omega is equal to 110 minus 12 TE. I hope you have these formulas. And we use these formulas. So whenever you have a question and linearization to find a new steady state value, to find the speed, the transient speed, this is what you find. First thing is to find the final steady state speed using this formula here. Now find K. Once you have K, you can find TM. Once you have K, you can find TM. And once you find TM, you can find omega t. Okay, so let's move on. Okay, I was giving omega to be what? Omega is 110 minus 12 t. Yeah, let's make t the subject. T will be equal to what? I'll move t here, move. So I'll get 110 minus omega all over 12. This is my TE. This is my TE given the question. And the question, they've also given me that at start, at t equals 0, the motor start with a load whose torque is, so TL is what? TL is 0.1 omega. L is given by 0.1 omega. Let me call it equation. And J is 0.5 kilogram meter squared. We're giving J to be what? 0.5 kilogram meter squared. Now, the first question is for us to find the what is to determine the final steady state speed. Final steady state speed. We know that to find the steady state speed, as the steady state, at steady state, what happens? We know that at steady state, what? TE is equal to TL. So what is TE? TE is 110 minus omega over 12. And this is equal to TL, which is what? 0.1 omega. So solve for omega. This is equal to 12 times 0.1, 1.2 omega. 110 is equal to, this will come here and become what? 2.2 omega. Omega is equal to 50 rad per second. So this is the final steady state. So I can write it as omega f. What is the final steady state speed given by what? 50 rad per second. 50 rad per second. First part of the question has been answered. Now the second part is that by linearizing the equation of motion, obtain the speed transient, that's omega t, and the torque transient. So now, we have all done this part, right? Let me clean now. All right. Now we say that the speed transient omega at t is equal to what? Omega f plus omega I minus omega f e to the minus t over tm. And we said to be able to find this, I must find what m is. I know what omega f is. I just found omega f to be 50. Omega f is 50 rad per second. Rad per second. I must find tm. Tm is what? J over k. I must find k. K is what? K is dt L d omega minus dte omega. So where is dtl, the omega? This is the dtl function here. If I differentiate with respect to omega, it becomes 0.1, the coefficient of omega. So 0.1 minus dte the omega. dte the omega. Differentiate this with respect to omega. I can write this function as what? As 110 over 12 minus omega over 12. Differentiate a constant, you get 0. Differentiate omega is the coefficient of omega. So that's what? Negative 1 over 12. So minus negative 1 over 12. Calculate that, Papa. So you get what? 0. Sorry. So you get 0.1. 0.1 plus 1 over 12. You get 11 over 60. You get 11 over 60. So that's k. So once I know k, I can put k into tm. So this implies that tm is equal to what? J, which is 0.5 over k, 11 over 60. Something was 0.5 divided by answer. That's what? That's giving me 30 over 11. So I can now put what I found into the transient speed. So omega at t is equal to what? Omega f. We found the final speed to be 50 plus. Now what's omega I? Let's go to the question and see. Question says that what? The motor starts with a load. So the motor is starting. As starting, it means initial speed is 0. It's starting minus final speed 50. Multiplying e to the minus t over tm. Comes to be 30 over 11. So 30, 11 can come to the top here. So this will give me omega at t is equal to what? 50 plus 50 plus this equals 0. So it becomes 50 minus 50 minus 50 e to the minus 11t over 30. So that'll be our answer. We went through all this. You get it? So all this was not really important. All you have to do was just to know how to get what you get. Does it make sense? I hope it makes sense here. So that's it here. So this is the minus 1.1 over 3 is the same as minus 11 over 30. Right? So we have the answer, the same answer as they have here. So that's speed transient. This is a speed transient here. The question says also find the torque transient. So now that we have the speed transient here, we can find the torque transient. Now, what's the electrical torque? Electrical torque is what? TE is given by what? 110 minus omega over 12. So to find the electrical transient or the torque transient, I'll just put the speed transient into the torque to get the torque transient. So this will give me 110 minus 50 minus 50 e to the minus 11t over 30 all over 12. So this will give me 110 minus 50, that's 60. This will become plus 50e exponent minus 11t over 30 all over 12. So that'll give us the torque transient. So that's it for that question. That's it for that question. So it's not difficult. Anytime you have a question like this, you just think of it systematically. You want to find this omega at t is equal to what? Omega f plus omega I minus omega f e to the minus d over tm. So first thing, find tm, j over k. You don't know k. What is k? K is what? dtl the omega minus dte the omega at the final speed. Once I have k here, I can find my tm. Once I have tm, I can find omega at t. With the question, they can say, okay, as you have the transient speed, find the speed at 2 seconds. It means just put 2 seconds here. So put 2 seconds here and simplify. That's all. So it could have been a continuing question. All right. Let's move on, please. Let's take the next question. The next question says that what? A DC shunt motor has a torque speed equation given by here Te is 500 minus 40 omega. TL is omega squared. Te is what? 500 minus 40 omega. TL is what? L is omega squared. Question says that determine the final steady state speed. We know how to find that one already. At steady state, E is equal to TL. So I create a 2. So I'll say omega squared is equal to 500 minus 40 omega. Omega squared plus 40 omega minus 500 is equal to 0. Mode 5, 3, 1, 40 minus 500. So you get speed to be 10. Omega 1 is 10 and negative 50. But speed can't be negative. So I'll take the speed to be 10 rad per second. So this is my final steady state speed. 10 rad per second. 10 rad per second. Now the bit that was is the operating point stable. We learned that for stability, the TL over the omega should be greater than what? T over the omega at the steady state point. So let's check. Let's find the TL the omega. The TL the omega is what? Is 2 omega. That's 2 omega at the steady state. So at omega is 10. So 2, 10, 20. Let's find the TE the omega. The TE the omega is what? Negative 40. Negative 40. So from here we can tell that yes, indeed, the TL the omega, which gave us 20, is indeed greater than the TE the omega, which gave us negative 40. Hence, operating point is stable. Hence, operating point is stable. So we are done with the B part. Now the C says that by linearizing the equation of motion, obtain the speed transient. Let's obtain the speed transient. So we said in order, what is the speed transient equation? First thing, you write it down. Omega at t is equal to what? Omega f plus omega I minus omega f e to the minus t over tm. What is tm? Tm is j over k. What is k? K is what? dtl the omega minus dte the omega at omega is equal to the final state, which is what 10 in this case. So at omega is equal to 10. When I found dTL the omega, what did I get? dTL the omega, I had 2 omega, right? Minus dt the omega minus negative 40. So omega is 10. So this is 20 plus 40. K is 60. Once K is 60, I'll put K here to find Tm. Tm is J over K. J is what? J is 6. So Tm is 6 over 60. That's what? 1 over 10. Once I have Tm, I come here. So it's like you're back solving. So therefore, my omega at T is given by what? Omega F, which is 10, plus omega I. Let's check from the question. The motor start. Once you see the motor start, it means omega I is 0 minus omega F 10 e to the minus T over 1 over 10. So 1 over the 10 comes to the top to multiply here. So finally, I get omega at T is equal to 10 minus 10 e to the minus 10 T. So this is it. If we're supposed to find the torque transient, so I'll just put this omega in place of this omega, and that would have been it. Or if they say, okay, find the speed at 3 seconds, it means I'll make this T 3 seconds. So here will be negative 10 times 3, negative 30, and I'll put it into the calculator, and I'll get the speed after 30 seconds. I'll get the speed after 30 seconds. So that's it. Okay, so that's it. That's it for this side. That's it for how we solve these mechanical transient questions. So that's it. I think that's it for this unit 2. Yeah. Okay, now the next thing is look at it. The next thing is bring us something called the traveling time. Traveling time of DC motors. Traveling time of DC motors. Traveling time of DC motors. After I also look at the traveling time of induction motors. Look at the traveling time of induction motors. Okay, now let's pay attention here. Okay, kindly pay attention here. So, what's the traveling time? Traveling time is defined as the time required to change the motor speed from one steady state operating point to another. It's an important quantity in drives such as robotics. The traveling time of an electric motor can be computed using the electrical model of the motor and the equation of motion. And the equation of motion. Let's move on to 5. Hold on a bit. Yeah. Alright, let's move on. So we are looking at the traveling time of DC motors. After we look at the traveling time of induction motors. Now, the traveling time of DC motors. we define what traveling time is: the time taken by a motor to change from one steady to another steady state value. Now, this can be considered for two cases. Let's take case A. Right. In the first case, we can consider this for a case where we don't neglect, we don't neglect the inductive reactance. We don't neglect the voltage drop in the inductive reactance. And I think it's the case where you neglect the voltage drop. All right. So let's move on. So let's take for the first case. In the first case, see, I have a V here, right? Supplying through resistor, inductor to the motor and back. So according to KVL, I can write that my V is equal to what? This E here. V is equal to E plus the current. So the current going through here is IA. Current going through here, so IA RA plus the voltage drop in the inductance L DIA E. Okay. Now we can simplify this, combine with the equation of motion to get an equation, a second order equation that defines how the DC motor will behave when changing from one steady state to another steady state. Let's come here. Now, so when we combine it with the equations of motion, all this is the mathematics. You move through, you move through, you move through, right? Move through here. What you must arrive at is this. This is what we want. This equation here. So memorize this equation. That's what you can do. That's what we must do. So when we don't neglect the inductance, then the squared omega dt squared plus RA over LA d omega dt plus RAJ, no, K phi squared over JLA. Sorry. K phi squared over JLA omega is equal to K phi V over JLA. K phi V over JLA minus RATL over LAJ minus RATL over, I've forgotten right now, LAJ. So this is what you must memorize. So all that mathematics just leads to this formula that we must know. That if the inductance is not neglected, then the equation describing the dynamics of the speed given by this. Okay. So let's see how this is used. Let's see how this is used. So this is a second order equation, a second order non-homogeneous equation that we are supposed to solve. Okay. So yeah, for the first, you solve the homogeneous part, which you equate it to 0 and solve it. And then you move on. So let's see. Let's take a question. Let's take a numerical example. A DC shunt motor has the following parameters. So we've been given K phi, RA, LA. So once we have LA, means LA is not neglected. Okay. The rated voltage of the motor is 600 volts. So at the 600 volts, motor has some speed at the 600 volts. No, that's the rated voltage. So the rated voltage of the motor is 600 volts. Now the voltage is reduced to 150 volts at starting. So it means at that starting at 150 volts, that is the operating voltage. This is the rated voltage, right? But if you are working with the operating voltage, the load connected to the motor is a constant torque of 20 Newton meter. So we know TL. We know J. We've been given the moment of inertia as that. Find the motor speed as a function of time. What that means is that get this expression here and solve this second order equation to get omega at t. So let's see. So first, you're supposed to substitute all the values into it. So d squared omega dt squared plus RA over LA. RA is 1, LA is 10 milli. So 1 over 10 times 10 exponent negative 3 d omega dt plus k phi squared over JLA. K phi squared. So k phi squared is 3. 3 squared 9 over JLA. J is what? J is 6. So k phi squared, which is 9 over JLA. 10 times 10 to the negative 3 omega is equal to k phi 3. D is 150. J is 6. LA is 10 times 10 to the negative 3 minus RA. RA is what? RA is 1. RA, L, we're giving the torque. The torque is 20. RATL, that's 20. Over J. 6 times LA. 10 times 10 exponents negative 3. So we have this. So you simplify this. You arrive at this equation here. We arrive at this. D squared omega dt squared plus 100 d omega dt. So we'll get d squared omega dt squared plus 100 d omega dt plus 150 omega plus 150 omega is equal to, simplify this side, you get 7166.67. 7166. So that's what your calculator work. Let me call this equation A. So we had to memorize this formula to be able to arrive here. So please kindly do well to memorize the formula. It's long, but you can memorize it. So we have it like this. Right? Now, the first thing you do is to find the final steady state value. The first thing you do is to find the final steady state value. And we said that what? We said at steady state, the omega dt, there's no rate of change. The omega dt is 0. So it means at steady state, this point goes to 0. It means there's no second change in, because if the omega dt is 0, it means the squared dt, the squared omega dt squared is also equal to 0. So omega f. So first thing, find final speed. Find final steady state speed. Final steady state speed. So from equation A, we said at steady state, here becomes 0, here becomes 0. So I'll be left with what? 150 omega is equal to 7166.67. So omega is given by what? 7166.67 over 150. So let's simplify that. Omega is 7166.67 over 150. That will give me what? 47.78. 47.78 rad per second. So this is my final, I can call this my omega f, my final steady state value. So that's the first thing you compute. Now, the second thing that you must compute, is you solve the homogeneous form of the equation. What that means is that equate this to 0, equate this part to 0, and solve it like a second order homogeneous equation. So we have the final steady state, so I can wipe that part off. Right. Now, so this part will still come back again. So that's what? The squared omega dt squared plus 100 the omega dt plus this. Right. So now, okay, 59 minutes. Sure. So I say equate this to 0. So do the squared omega dt squared plus 100 the omega dt plus 150 omega is equal to 0. So now to simplify this, to solve this second order, just change it to a quadratic. So again, m squared plus 100m plus 150 is equal to 0. So let's solve this for what m is. So 53, 100, 150. So you solve the quadratic. Yes, you just solve the quadratic. So I'll get m1 to be negative 1.52 and m2 to be, oh, I'm doing the right thing. Yeah, m2 is negative 98.48. Negative 98.48. Okay, so this means that my omega t is my, so the question says that what? The question says that find the motor speed as a function of time. So that's omega t is equal to the final value. We had a final value, so it's equal to omega f plus a e to the m1 at t plus e to the m2 at t. So my omega at t is equal to what? Omega f. Omega f, we had it to be 47.78. 47. Oh, man. 47.78 plus A E M1 is what? Negative 1.52 plus B E negative 98.48 T. So now we are making progress, right? Now we have omega T, a function, yes. The next thing is to find what A and B are. So systematically, first thing, find your final steady state speed, which we did. We just equated this part of the function, this part, and found what the omega was. Second thing is to solve the homogeneous form. So equate this part to 0, make it a quadratic, and find the roots of the quadratic. And those roots become what your M1 and M2 are. So right now we have this function here. Let me clean everything and write that function at the top. That's where we are now. And now we are the fact that omega at t, which is the as a function of time, is equal to 47.78 plus a e to the minus 1.52 t plus b e to the minus 98.48 t. We have it like this, right? Now I can find an expression. So I need two expressions to be able to find what my a and b are. What is the first expression I can make? Now, when time is 0, the motor is now about to start. When time is 0, can I say the speed is 0? Yes, the motor is at rest. It's at rest. So, as starting says that the voltage is reduced 150 as starting. So, the motor is starting. So, as starting, speed is 0. So, I can use that to get a first equation that as starting, t is 0. Omega at t is also equal to 0. So I can get 0 is equal to what? 47.78 plus a e to the 0 plus b e to the 0. This will give me 1. This will give me 1. So I will left a plus b is equal to, I'll move this here and get negative 47.78 equation 1. Negative 47.78 equation 1. Equation 1. So that's the first equation I can write. All right. Let's see how we can get our second equation. I can clean this now. So now this is my omega at t. Let me find the omega dt. So to find your second equation, find the omega dt. This will go to 0. So here I'll be left with negative 1.52a e to the negative 1.52t minus so plus negative 98.48 e to the e must come here e to the negative 98.48 t. This might be omega dt, right? This might be omega. Now I know that what Te is equal to L plus J d omega dt. Te is what? Te is equal to K phi Ia. TL plus J d omega dt. Now I can have what? K phi IA over J is equal to TL over J plus the omega dt. Right? I can say my d omega dt is equal to what? K phi IA over J plus TL over J. I hope this makes sense now. Right? So now let's find the rate of change at starting. Let's find the rate of change at starting. Now, at starting, you know that the current is 0 at starting, just before the motor starts. So the current goes to 0. Let me clean this here. So I can solve it at the top here. So now let me find the omega dt just at starting. So at starting, this goes to 0. Right? Sorry, this is supposed to be minus here because I'll cross it. It's supposed to be minus here. Sorry, here. It's supposed to be minus here. And it's plus here. It's supposed to be minus here. There's plus here. That's supposed to be minus here. Yes. So I'll be left with minus TL as starting over J. As starting, the torque is still the torque, right here. So the omega dt at starting is given by what? The torque, which is what? Negative. The torque is 20. J is 6. This will give me negative 3.33. This will give me negative 3.33. Which means that for this function here, as starting, when t is equal to 0, I can have another expression. So when t is equal to 0, the omega dt is what? Is negative 3.33. So I'm left with when t is 0, this becomes 1. So a minus 98.48b, equation 2. So equation 1 and equation 2 can be solved simultaneously. And I'll get my a to be minus 48.49 and b to be 0.71. So I can write my function of time as initial velocity, final speed, which is 47.78. You see, we had a e to the m1 at t, so minus 48.49 e to the minus 1.52 plus 0.71 e to the minus 98.48 t. So that's it. So that's the expression that you get in the end. That is the expression that we'll get in the end. Okay. So that's it. So that's what was done here. That's what was done here. Yeah, so we have a final expression as this. And to find the motor speed after 5 seconds, you just put in 5 at where you see t. And that you just simplify it with your calculator. That's all. That's it. So we'll end this video here. We'll continue another time. Thank you.